Huh? 19/28. One point two, problem 19. So 19, graph the function and its parent function, then describe the transformation. So we're not worried about graphing, we just want to describe the transformation. Now, the only thing that we have is this 1/3. And since it is linear, the linear form of this is our a parentheses x minus h plus k. No, you don't have to write that. I'm just writing it so we can kind of line it up and compare it. We have no h value because there's nothing in parentheses that's being added or subtracted. We have nothing added on to the end. So all we have is this 1/3 that's taking the place of a. Now, if it's negative, then it's a reflection across the x-axis. It's not negative, so there is no reflection. So the only thing we have left with that is a vertical stretch or shrink. Now, because 1/3 is between 0 and 1, it is a shrink. If a is greater than 1, it is a stretch. Or not stretch. 1/3 is shrink. 1/3 between 0 and 1. Now, if it was 3, it would be a stretch. I spaced out there for about half a second. So, vertical shrink between 0 and 1. 1/3 is between 0 and 1, so it's a vertical shrink. If it's greater than 1, it is a stretch. Now, with vertical stretch and shrink these here, I do want you to write it out. So, I don't want you abbreviating it, but please make sure to write it out. Yes. And if it is a stretch or shrink, I would like the amount that we're stretching or shrinking by. So not just vertical stretch, vertical shrink. We need that. And if it is a reflection, make sure to specify if it's across the x-axis or across, well, it's just mainly x, but just reflection across the x. Yeah, there are, let's see here.
19, 21, 23.
No, those are just vertical stretch shrink. And we wanted to look at 28. Okay. 28. From the same one, h of x is equal to negative x plus 5. Now the negative is our reflection across the x-axis. Now specifically, it is going to be across the x-axis. Even though we don't have one across the y, it's still good to go on and write it out because there is one across the y. And the only other part we have is the plus 5, which would be up 5. If it's inside parentheses or absolute values, it's our left to right when we're adding or subtracting a number. If it's outside, it's up or down. Let's see here, use a graphing calculator to graph the function's parent function. Then no, so just then describe the transformation. The only ones that you needed it on were 3, 4, and 5. Because in exercise 3 through 6, identify the family to which the function belongs, then compare the graph, so then describe it. So 3 through 5 are the only ones that really needed it, but since I didn't put an emphasis on it, if you put it, awesome. If you didn't, I'm not counting off. All right? And for the most part, for me to take points off on some of these, especially that have more than one part, is you got to miss at least half or a little bit more before I start taking points off, or some combination. If you do have questions. So then describe the transformation. So 3 would be a vertical stretch of 2, left 2, down 8. So you're doing the same thing. They just gave you the graph. So 28 and 3. The only thing we didn't do on 28 was tell you what parent function it was. So what you would do for 28, you would also do for the others. Does that make sense? try those. If you do have questions, we can go over those a little more. Because essentially for 3 through 4, you're going to do exactly what we did here, and then you just give what the parent function is. Does that make sense? Okay. And again, homework is due at the end of the chapter, for chapter 1 is due at the end of the chapter 1 test. But also, I would stay on top of it, get it done when you can. That way you're not trying to do everything all at once at the end. Yes, sir? Okay. Just make sure to put it back. I believe this is where we ended yesterday, or Friday, yes? Because we got to the one above it with the up 5, which really just ended up putting plus 5 at the end. F of x equals the absolute value of x minus 3. Translate 4 units to the right. So I think we're on the back of the first page at the bottom. Yep. So since we're going left to right, the general form of this is f of x minus h. Now they didn't give us a name for the new function, so we can name it whatever we want. So someone give me a letter. C. So our new function will be c of x. So we just got a name for it. That's all we need to do. So c of x equals f of x minus h, where h is our movement to the left or right. So c of x. We just picked a name for it. Yep, so f of x minus h is the general form for our left or right. So for horizontal translation, when we're moving it left or right, our general form is at f of x minus h, where h is our movement left or right. Now the c of x is just a new name for our function, so the one we applied the transformation to. Here, they didn't give us anything, so we just picked c. There is no rhyme or reason for picking c, we just decided today we're going to use c. Now our h value, how far are we moving to the left or right? 4. And we're going to the right. Since we're going right, 4 right is positive. Because since we're not putting it in the function yet, left and right still behaves as we're used to. Right is positive, left is negative. Does that make sense? Because once it's inside the parentheses, it looks the opposite. So when we replace the x value into the function, or plug it in, we have f of x minus 4. F of x minus 4. Well, now it is that opposite, because even though it's going right, inside this function it looks negative. Questions on this here? All right. This is still our c of x. Now our f of x equaled the absolute value of x minus 3, yes? Well, we don't have f of x anymore. We have f of x minus 4. We have the whole expression. So we replaced this x here with x minus 4, which means every x in the function has to be replaced with x minus 4. So we'll still have the absolute value, but instead of x, we have x minus 4 minus 3. So all we do is take out every x in the function and plug in the x minus 4. So it's ever f of whatever's in that parentheses is going to go in every place of x throughout the expression. We can. So I did it this way because on Friday we were talking about where the f of x go. So it's still here, it's just this is equal to it. So they are equivalent. So all we're saying is f of x, this function, this is what it's equal to. This is its new function for given our general form. So there is actually no solving. We simplify. We won't get a number answer. So it's not going to just end up being 5. So we simplify and just have an equation that we end up with. Now with our simplifying, well, here are x minus 4 in parentheses. Is there anything in front of the parentheses besides the absolute value? There's not a number, there's not a sign, nothing to take care of. So we can take away the parentheses. Now, it is going to be very tempting to want to combine our like terms of -4 and -3. But because of that absolute value bar between them, they're not really like terms. We would have to simplify the absolute value, what's inside it first, and then subtract 3. So this is actually simplified. That is the final answer. And this here would be equal to c of x. That is our new function. Is c of x and f of x minus 4 are the same notation as what we have applied it to. So this is our function. Questions on this here? We ready for the next one? Our next piece is reflection across the x and reflection across the y. And there is a lot of extra information here. But the key thing, especially when applying it to the function, are these two pieces here. If it's a reflection across the x-axis, we're taking negative f of x. Crossing axis, negative f of x, which is saying whatever the y value or the output value of is, it's going to go from positive to negative, or negative to positive, or multiplying the outputs by -1. Reflection across the y, f of negative x. We're multiplying all the inputs by -1. Changing their signs. But the key thing, again, are these two pieces here. That's what's going to be key for applying this reflection across the x and the reflection across the y. And as long as we stick with those, it'll be fine. And I definitely need to go back and update these. So the first one here, when we were talking about reflections, let f of x equal the absolute value of x plus 3 plus 1. Write a function g whose a reflection in the x-axis of the graph of f. So let me start off with g of x, because that's what they told us to name the new function, g of x. G. And we want to write a reflection across the x-axis. So again, they told us the transformation we want. So I would go over to my list and see what is the general form for reflection across the x-axis. Well, it's negative f of x, negative of our function. So here, we'd fill in the general form, negative f of x. Because again, these general forms are mainly roadmaps to help us apply the transformation, tell us and help us see what's going to change. How is it going to change? So we're saying negative f of x. Questions on this here? So we still have f of x, yes? So we didn't do anything inside, so we can replace f of x with its function. It's going to be equal to it, too. So we have negative, parentheses. This is the first one where we've really needed that parentheses, because that negative is not being applied to just one part of that function, it's being applied to the entire thing. So we'd have absolute value of x plus 3 plus 1. Now we can say we replaced every x and f of x with x, or we just replaced f of x with its function. If it was x minus 3, I'm guessing what you're saying. Oh, if we did it the other way, yes? If we're doing y? Okay, so you're talking about negative with the absolute value, yes? Kind of how is it going to apply? Yes. Right, talking about so I'm just rephrasing. Talking about how the signs would work inside the absolute value with the fact that the absolute value normally comes out positive, yes? And here, the negative won't go inside. So when we multiply this next step and we apply this negative through, the negative will apply to the number in front of the absolute value. Does that make sense? So the number in front of it's not written, but it's understood to be 1, which when we apply it to that 1, it's going to become negative 1, or really the absolute value is negative absolute value of x plus 3. Because we can't take the negative inside. Because if we did, that reflection across the x would be completely undone. It would remove it. So it has to stay out front. But that negative can be applied to the 1, which turns it from positive 1 to negative 1. We're essentially multiplying the whole function by negative 1. So we multiply in front of the absolute values. So it goes from positive absolute value of x plus 3 to negative absolute value of x plus 3. And our positive 1 goes to negative 1. And that's it. Now the reverse is kind of also, for the most part is true. We can't pull the negative out. If it was negative x inside the absolute value, or negative x plus 3, I can't just pull the negative out. Yep. Yeah, no, all the transformations, we're not going to have a numerical answer. It's not going to be x equals 4. Here, we just get equations. Yep, that's as far as it goes. Yeah. Any other questions on this here before we look at across the y? We good with this here? All right. So, write a function h of x whose graph is a reflection of the y-axis of the graph of f. So I rewrote it again just so I can have it here. I'm not scrolling up and down. Okay. So which transformation are we talking about? Well, for like reflection across the y-axis, yes. The general form is what? F of negative x. Now the f in all of the general forms is just, we picked it because that's normally the one we're applying it to. It doesn't have to be f, because if we did it in between, we could do this with g of x, h of x. It's just a letter. What function are we applying it to? Because up to this point, we've just been applying it to f of x. So it's just a letter taking a place at this point. Do we have f of x anymore? Well, no, we have what? F of negative x, yes? We replaced every x in the function f of x with negative x, because we replaced this x with negative x, which means every x in the function has to be replaced with negative x. So the absolute value of x plus 3 plus 1, it's up a part of a. So it's still talking about the same function. Yeah. Good question. So we're replacing this x with negative x plus 3 plus 1. Now the question that probably some of you had, why do I keep putting parentheses around it? And that is because if, instead of it just being x plus 3 inside the absolute value, it would say 3x plus 3, that 3 would have to multiply by the negative, which would just give us negative 3x. But if it was, say, negative x plus 3 inside, we'd have negative parentheses negative x, close parentheses. It has to be applied to it. Here, we don't really, it doesn't hurt us if we don't have them, and it doesn't hurt us if we do. It doesn't impact it either way. The main rule I will stick by, especially with the notes, is I would always rather to have them and not need them than need them and not have them. Because if it turns out, as we've seen so far, we didn't need them, we can drop them, we can move on. So it's a good, consistent, it's a good habit, especially in the graphing or either calculator. But questions on this here? I feel good with this here so far. Yes? And yes, I need to go back and redo these slides because I don't think they look too grainy or pixelated where you're all sitting. But if you're standing right next to them, they're even worse. Yes. Let f of x equal the absolute value of x minus 5 minus 4. Write a function h. So this time we're starting off with h of x, whose graph is a reflection in the x-axis of the graph of x. So again, general form for reflection across the x-axis is negative f of x. Negative f of x. Now we still have f of x, we've just applied a negative to the front. So the first thing we can do is replace f of x with its function. And this is, again, one of the cases where we really do need those absolute, or those parentheses, because the negative is not going to be just applied to the absolute value of x minus 5, it's also going to be applied to the negative 4. It has to be applied to each part of it. We good on this part here. All right. Now when I apply this negative, we'll apply it or multiply that negative by the absolute values, not through it, but just to it itself. So I multiply that absolute value by the negative, by that negative 1. It just becomes negative absolute value of x minus 5. Negative stays out front. So when we multiply the 4 by it, it was negative. Now it's positive. Because our negative times a negative makes a positive. That's it. Yeah. Yes. Yeah. So, and again, that's because a lot of times we're used to coming up with a number one thing, but it's going to end up just being an equation. Actual numerical answer. The one thing with these here, you know you're finished when you cannot combine or reduce anything. So there are no like terms, either both inside or both outside the absolute value. And there's no, it's just simplified. Does that kind of make sense? Because we are used to getting a number, 4, 7, but here we get an equation. Yes. And there are some problems with systems of equations where you given two equations of a line, algebra 1, where you found where they intersected across. There are some systems of equations where your answer is an equation. But we won't delve too much into that here. Let's look at this one here. Let f of x be the same function we're working with. This time g of x, we want to write a function g whose graph is a reflection in the y-axis. What's our general form for y-axis? F of negative x. F parentheses negative x. Yeah, you're good. Yes. So we would, in essence, drop it down and replace every x in f of x with negative x. So we'd have absolute value negative x minus 5 minus 4. Since there's nothing in front of the parentheses, it'll just say negative x minus 5. Yes. That's it.
Okay.
11:16.
I wrote down the final four.
Yep. Yeah, because here the parentheses aren't needed because we can drop them and be just fine. Whew. Yeah, that's what I was saying. Yeah, the original slides when I did these, there was only so far I could zoom in and I had to make them bigger because these were all set up for the smartboard. So having them in some of the smaller fonts, it didn't work well and the resolution didn't work well. I need to go back and just redo them. How do we feel about reflections across X and Y? Do we need another example of these here? Or do we feel comfortable with these? Good. Okay. The last two that we have are vertical stretch and shrink and horizontal stretch and shrink. Let's start with vertical. Okay. So they gave us, we have two, vertical stretch and shrink. It's a stretch if A is greater than 1. It's a shrink if A is between 0 and 1, which we had from the other one. Now, if you notice on the notes, for vertical stretch and shrink, we only have one form. It's A times f of x. Stretch or shrink, it's the same form. Does not matter. A times f of x. Because if it's a shrink, we're just going to use whatever that value is in place of it. If it's a stretch, we use that value. Does that make sense? Yes? Okay. Horizontal. Stretch. Flip. Horizontal stretch or shrink. Stretch slash shrink. Flip value. Then plug in to f of b times x. So here, so our general form for horizontal stretch and shrink is right there. F of, it calls it a times x, the amount that we stretch or shrink. So the horizontal stretch or shrink by a factor of 1 over a of the graph of f of x. So if it told us that it's a stretch of 2, flip it. It's 1/2. Whatever the horizontal stretch or shrink is, we have to flip it. So if it's a fraction, top becomes bottom, bottom becomes top. So if it's 2, what's the denominator? It's understood to be 1, yes? So it's really this. So if we flip it, it becomes, then we plug that in. This is really the only one that's tricky, especially with these here, is we have to flip it. And that's true even if we were looking at horizontal stretch or shrink, because if it's 1 over 2 times x inside, when we take it out, we have to flip it, so it's going from 1/2 to 2, so it's a horizontal stretch of 2. If it's a whole number 2 inside there, we've got to flip it, giving us 1/2, so it's a horizontal shrink of 1/2. That's the only one that's tricky, because horizontal stretch and shrink, we got to flip it before we plug it in. And if we're bringing it back out, we've got to flip it again to know what it's actually doing. Let f of x equal the absolute value of x minus 3 minus 5. Write a function h of x whose graph is a vertical stretch of the graph of x by a factor of 2. So vertical stretch, vertical shrink have the same form of a times f of x. Where a is the amount that we're stretching or shrinking the function by. And it would be 2. So first thing we're going to do is plug 2 in for a. Now our function f of x is still, well, f of x, yes? So, yes. So we're going to replace it with its function. Our absolute value of x minus 3 minus 5. Questions on how we got to this point here? Now, just like with the negative, we're going to distribute the 2. Just like with our negative f of x, we're going to do the same thing, but instead of a negative, we have a 2. Now, just like with the negative, the 2 is not going to multiply inside the absolute value. So it's going to be 2 times the absolute value of x minus 3. Then we're also going to do 2 times negative 5, which would be negative 10. Yep, we just doubled everything. And that's it. Questions on this here? And vertical shrink will essentially behave the exact same way. Yep, because vertical stretch, vertical shrink, a times f of x. So we just replace a with that value. Now the next one. Write a function g whose a horizontal shrink of the graph of f of x by a factor of 1/3. Yes. Now for horizontal stretch and shrink, we have f of a times x. So we have that a times x inside the parentheses. Now horizontal stretch or shrink, this again, this is the only one we have to do anything to that value before we plug it in. Because left, right, just like it was, if it was to the right, that value that was going in was positive. Left was negative, up positive, down negative. Vertical stretch and shrink, we just take the number itself. Here, we take whatever the factor is with horizontal stretch or shrink, and we have to flip it. Since it was 1/3, it's going to become 3/1. So our a value in this case would be 3. Because we don't write 3/1, we just write 3. And the first thing we can do is take that value and replace a with it. So we have f of 3x. Questions on this here?
So with 3x, would you equal put 3x with
So just like we did with or reflection across the y-axis, where we replaced every x in f of x with negative x, here we're going to replace every x in f of x with 3x. So we have parentheses, 3x minus 3 minus 5. Now, since there is nothing in front of the parentheses with 3x, we can drop them, giving us this here. Absolute value of 3x minus 3 minus 5. And that's it. There's as far as we can go. 3x and negative 3 are not like terms, so they won't combine. The negative 3 and negative 5 technically are like terms, but because of that absolute value bar, they can't interact with each other.
All the differences.
So that's
Yeah.
all it is.
Yeah. And the biggest thing, because again, we're going to finish this out, probably it's going to be tomorrow, with doing more than one, but even doing multiple of these, just take it one of the general forms at a time as we apply it. Now, with horizontal stretch and shrink, clear, math, number, absolute value, x minus 3 minus 5. So this is the function we have, yes? Now, for horizontal stretch or shrink means x-axis. Since it's a shrink, it'll be increasing slower along the x-axis. Math, numbers, 3x minus 3 minus 5. So it does end up, for some reason, shifting it, but if we look at the way that it's expanding out, is at a slower rate than it was before. Questions on this here? Yeah, so this horizontal stretch and shrink is one of the things that is a little funny in how it works. But that's it there. And it is odd that it does move it over, but if we look at the width of it, it is increasing slower than the one in black, yes? So horizontal stretch means it's going to open wider. So it's kind of like vertical stretch, not really. It's going to increase fast vertical if it's in whole number. But we ready for the next one? Write a function g whose graph is a vertical stretch of the function f by a factor of 5. Vertical, or sorry, horizontal. I just skipped right over that. Yes. So the general form would be f of a times x. Now, since we're talking about horizontal stretch or shrink, we need to switch it from 5 to 1 over 5. So our a value, the number we're plugging in, is 1 over 5. So whatever value it is, if they give us 5 for horizontal stretch or shrink, we flip it to 1/5. Now at this point here, we can plug in that value in for a. And just like we did on the previous one, we're going to place every x in f of x with 1/5 x. So add parentheses. Instead of x, we have 1/5 x minus 1 plus 2. Yep, drop the parentheses because there's nothing in front of it. And we're done. Questions on this here? We ready for the last one for today? We'll finish these tomorrow. Write a function h whose graph is a vertical shrink of the graph of f by a factor of 0.25. Vertical stretch or shrink. The general form is a times f of x. Vertical stretch or shrink, we don't have to do anything to our value of a. And for us here, a is 0.25. And even though it's a shrink instead of a stretch, doesn't matter, vertical, replace a with its value, which gives us 0.25 times f of x. X minus 1 plus 2. Questions on how we got to 0.25 parentheses absolute value of x minus 1 plus 2. We feel good with this here. Now the last thing we need to do before we do any simplifying or finishing this up, we do need to distribute the 0.25. Now for our absolute values, it really doesn't do much because there's not a number in front of the absolute values besides 1, which 1 times 0.25 is just 0.25 times our x minus 1. So 0.25 times 2. So, yep. So 0.25 times 2, or 2 of our 25s, give us 50.5. And that's it. That's all we have to do for this here. Questions on any of this here? So, because we do have two more with horizontal stretch and shrink, vertical stretch and shrink. And then we're going to do some that have multiple. I'm going to go on and post this assignment up there in Google Classroom so that you have it. Because the first, I think 3 through 6, 11 through 14, and 17 through 20 are just doing one or the other. Essentially everything we've done so far. Yep. Sorry. Yep. 3 through 6 is our up, down, left, right. 11 through 14 is just reflections across X or Y. 17 through 20 is our horizontal stretch shrink. So 27 and 29 are the only ones we haven't done yet of multiple, but you can do 80% of this already. We've covered 80% of it. We'll finish up the last bit tomorrow. Yep, 27 and 29.